Okay. Hello, everyone, to the last of the lectures on Galois representations for CTNT 2022. So, you are by now experts on Chebotarev because of Keith's wonderful course on Chebotarev density. So remember that at the end of the last lecture, what we were doing is actually use Chebotarev to compute images of Galois representations. We don't know a lot of elements of the absolute Galois group of Q, but we saw that actually using Chebotarev, this is the finite version of Chebotarev, you can actually prove that the Chebotarev elements are dense in the absolute Galois group of Q. So the hope is that by sending Frobenius elements through Galois representations, we can actually make sense of the images and maybe compute some of the images of Galois representations. And so images of Frobenius elements are important because of that. Remember the setup in the infinite case, we have a prime, and then we pick a maximal ideal of the integral closure of the integers lying above P. Then we can construct the Galois group. We can construct a decomposition group at the level of the absolute Galois group of Q. Similarly, there is an inertia subgroup that is a very large inertia subgroup that is inside decomposition. But the point is that it still happens that the decomposition group surjects to the absolute Galois group of the finite field FP. There's a Frobenius element there that is not a generator, it's a topological generator. I made a note here that, for example, 1 is not a generator of the p-adic integers, but it's a topological generator of the p-adic integers. You can get as close as you want to any other p-adic integer just with a multiple of 1. Okay, so we don't get all of it, but we do get a topological generation. So since there is a rejection here, we can find a Frobenius element attached to this prime ideal p hat that lands on Frobenius. Okay, so those are the elements that set of those elements is dense in the absolute Galois group of Q. And then we saw that then we can see and one can compute, I think Keith did this, to compute where does one Frobenius element land? Well, in Z mod LZ or Z mod L to the n, it lands in the congruence class of P. So when you go all the way up to the L-adics, it actually lands on P, on the actual number P as an L-adic integer. And so Chebotarev on one hand tells you that these elements are dense in absolute Galois group of Q. So I can get as close as I want to any element in here and know where it lands. And on the other hand, it lands on primes, and these primes, thanks to the Dirichlet theorem on primes and arithmetic progressions, they can get as close as you want to any L-adic integer. So in this sense, in the sense of topology, we can understand all the values of this Galois representation. By the way, this is for primes that are not L, and we want that so that what happens is that, well, the inertia at P is always in here, but what happens is that this Galois representation is actually, what we say, unramified at P if P is not L, meaning that inertia is actually in the kernel of the Galois representation. So actually, Frobenius elements in the Galois group are defined up to elements of inertia. But if inertia is in the kernel, then it doesn't matter what choice I made of a Frobenius element, they all go to the same place. And the Frobenius elements in here, we'll talk about this in a second, they're defined up to conjugation, because if I conjugate the prime above, then I get another prime below, I get another prime lying above my little p. So these are defined up to conjugation here. So I think we'll talk about that in a moment. And so in any case, yeah, so those Frobenius elements are defined up to conjugation, and we'll see how that plays a role when we go up to two-dimensional Galois representations. Here's another example that we saw last time. We talked about Artin Galois representations, and we decided that actually they all come this way. They are all, you choose a number field, and you first restrict to that number field that is Galois, and then see how Galois acts on that number field, and then you follow with a representation of a finite group, which is this finite Galois group. Okay, and we saw that these are actually the irreducible Galois representations of S3. And so what about Frobinii? How do they travel through these maps? Well, we can see what happens. So take a Frobenius element of the absolute Galois group, and what's going to happen is that it's going to first map to this Galois group, and it's going to be, when you restrict, you're going to get a Frobenius element. Chebotarev tells me that I hit every element of this Galois group, of the finite Galois group. So now I'm actually seeing that every Frobinii hits one of the elements of S3, and now I can compute where they land. How am I going to do that? Well, what I was saying before is that the Frobinii are defined up to conjugation in here in the absolute Galois group of Q. So when I go all the way to, say, matrices, the best thing I can hope for is a conjugation invariant, so that I know that invariant is actually sort of something natural to study in the conjugation classes of Frobinii elements. So the trace of a matrix is actually invariant under conjugation. So that is a good thing to study. So for example, in this, when you have a trivial Galois representation, then it only goes to the identity, the trace is 1, then you know that every Frobenius element goes to 1. What about if I send you a Frobenius and I tell you what the trace is in this representation is still one-dimensional, but it's non-trivial? Well, it turns out that the trace of sigma would go to 1, and the trace of tau would be -1. So I can actually, by the trace, I can determine what is my image of Frobinii. Okay, so if I somehow figure out what the trace is for a Frobenius element, I know where I'm going. And in the two-dimensional representation that we got, you see, well, the trace of the identity matrix would be 2. The trace of this matrix is -1, and the trace of this matrix is 0. So you see that the trace actually determines what image I have. So if I tell you I have a Frobenius element whose trace through this Galois representation is 0, then I know what image you're talking about. So I know where that Frobenius lands. It will land in a reflection. So it turns out that that is not just something nice about this example. It happens in all Artin Galois representations. So we're going to call semi-simple a representation that is, if it is a direct sum of simple irreducible representations. Okay, so it turns out that Artin Galois representations are determined by the values of the traces of Frobenius. Okay. Oh, here I'm allowing, actually, you can throw away any finite set of primes. You throw any set of primes, any finite set of primes you want, but then you tell me where Frobenius lands, and you only tell me the traces of where they land. I can actually tell you what Galois representation you're talking about. It turns out that I can go backwards by knowing what are the traces of for each prime, what's the trace of the image. I can go back, and how do I determine an Artin Galois representation? I need to know what is the field, the number field that it factors through, and what is the group theory representation that gives me. So I can actually go back and determine both just by doing traces. When you move to an elliptic Galois representation, it turns out that traces are still good, but I have to then choose a semi-simple. It has to be on a semi-simple elliptic representation. It has to be a direct sum of simple representations. We'll see in a moment one that is not. So is determined by the values of the trace of Frobinii in unramified places. By the way, like I said before, we're working with unramified places. These Galois representations, the Artin Galois representations, are ramified only a finite set of primes, and the examples that we've seen coming from geometry, they're ramified only at a finite number of primes. So those you could throw in these finite set of primes anyway. Okay, and if you have a mod L Galois representation that is semi-simple, it is also determined by the values of Frobenius. However, you need the prime, if it's in characteristic L, the prime has to be bigger than the dimension of your Galois representation. Otherwise, sometimes there's just not enough information to determine the Galois representation. Okay, so let me go then to Galois representations of elliptic curves, and then we'll come back to see how we can, if we can determine Galois representations of elliptic curves using this trick of traces of Frobenius in a moment. So remember that we constructed, for an elliptic curve, we constructed what we call the Elliptic Tate module. So an inverse limit based on the multiplication by L maps on L power torsion. And then we also constructed what we call the Tate module, or the Adelic Tate module of the elliptic curve, which is the same, so for an inverse limit, but over all torsion. This is a way to capture the structure of all the torsion elements on an elliptic curve. And Galois acts on these Tate modules. Okay, so then those give me an Adelic Galois representation attached to an elliptic curve, an Adelic one, and mod L representations attached to E that are related by simple reduction mod L, or reduction to, or projection to an Elliptic component. Great. So so what happens with Frobenius in this case is that if you have a prime and an elliptic curve of conductor n, the conductor of an elliptic curve, I think it came up in one of the, at least in one of the talks. So the conductor of an elliptic curve is it's essentially the primes of bad reduction. So primes where when you reduce your elliptic curve mod P, the reduction curve is no longer a curve. There's some, all of a sudden, some singularity, and to some powers that indicate how bad that singularity is in some way. So in any case, so it turns out that the Galois representations attached to elliptic curves, they're also ramified only a finite number of primes, the Elliptic ones, and they're unramified at every prime that doesn't divide L times the conductor. So the bad primes for the Galois representation, for the Elliptic ones, if it's Elliptic, it's L, and the primes dividing the conductor, the primes of bad reduction. Otherwise, it's the representation is unramified, which means that the big inertia groups at P are in the kernel of the representation, which is great because, as we talked in with Christelle, ramification groups in higher inertia groups are very hard to deal with. So the more of them that are in the kernel of your representation, the better off you are. Okay, so so then what happens if I send over a Frobenius element? I'm not going to tell you what the matrix is, but we have information about the characteristic polynomial, or the characteristic equation of the matrix that is in the image. And it turns out the characteristic equation elliptically is this one. And if you reduce your equation modulo L, then you get this equation modulo L. So it gives you information. Well, you know that in the characteristic equation, this is the trace of your matrix, and this is the determinant of your matrix, right? So that is great. So now here, the trace of your image, which is actually what I was trying to get at, it's right here. And it turns out this, which is not very surprisingly called, this number is called the trace of Frobenius. It might be surprising that sometimes in elliptic curves classes, before you know anything about the Galois representation, before you know about the images of Galois representation, or even before you know about Chebotarev and Frobenius elements in the absolute Galois group of Q, we call this quantity the trace of Frobenius, just to keep track of where that comes from. And you can define it very simply. It's just P plus 1 minus the number of elements of your elliptic curve reduced at P. Remember that P does not divide the conductor, so P is of good reduction. So this is an elliptic curve itself over FP, so I can compute the number of points, and that is what we call the trace of Frobenius. So there's a very simple way of understanding what's the trace of Frobenius. And moreover, the Galois representation is irreducible. Okay, so it is one simple component. They will be, the Elliptic ones are irreducible. When you reduce mod L, it need not be irreducible. So here's an example where you have an elliptic curve just given by y squared equals x cubed minus 2. The conductor of that elliptic curve is exactly 12 cubed. So it's bad at 2, it's bad at 3, good everywhere else. Fantastic. And I'm going to look at the mod 2 representation. So this is not the two-adic representation, it's just the mod 2. And it turns out we'll see the mod 2 representation is not irreducible. If I went to the two-adic representation, is irreducible over Q. So here, the two torsion, so the two torsion of an elliptic curve is actually, if you have it in this short value stress form, the two torsion is given by the zeros, so alpha comma 0, where alpha is a root of the polynomial in X. So it's these elements, the point at infinity, and then alpha comma 0, where alpha cubed minus 2 is 0. So here are the 3 points of exact order 2. The square root of 2, the cube root of 2, sorry, is 0. The cube root of 2 times a third root of unity, and the cube root of 2 times the square of that root of unity. Those are the points of two torsion. So then what we call the two division field, so the field of definition of the two torsion will be, I need the cube root of 2, and I need this, so I need the square root of minus 3. And this field is actually Galois. That's another property, that division fields are actually Galois over Q. So the Galois group is S3, which is one of those exceptional isomorphisms, just because there's not that many groups of order 6. So it actually is isomorphic to GL2F2, which is what we would call the automorphism group of the two torsion. So the image of this Galois representation is actually surjective. So now I know that my image is all of GL2F2. I'm sorry, this Galois representation is irreducible mod 2. I'll have another one later that is reducible mod 2. So in any case, S3 is generated by two elements. So I just need to know, to understand better what happens is I need to know where each element goes to construct the image. So here, sigma, remember, is the one of order 3, so it's the one that permutes the cube root of 2. So it will send this to another conjugate, so it sends P to Q, okay? And also Q, it will permute this one to another root of unity times this, so it actually sends it here. So Q actually goes to P plus Q. And if you put that in terms of matrices and in terms of the basis P comma Q, that means that P goes to Q and Q goes to P plus Q. So that is what that matrix represents. And tau fixes P, and tau sends Q to P plus Q. So it's this matrix instead. So that gives you what the image is. The images will be, well, the image of sigma and the image of tau. And these two elements generate all of GL2F2 S3. So I've built the image exactly as where these elements go. Now remember again that the Frobenius classes are defined up to conjugacy. The Frobenius classes are well defined up to conjugacy then in GL2 of F2. And the trace of the Frobenius elements is a conjugacy invariant. So I need to know what are the possible conjugacy invariants and then check. By the way, also we know that the trace of Frobeni is given by this characteristic equation, so that whatever the matrix says that this image is, it will satisfy this property, and the trace of those matrices has to be P plus 1 minus the number of elements. So I can compute that and see that, well, where does the identity has trace 0 mod 2, because it's 1 plus 1. Tau has trace 0 mod 2, so you see I can't distinguish those two elements modulo 2, because just knowing the trace, I can't tell them apart. This is because, remember, like, even though this representation is irreducible, for a mod L representation to be able to tell apart Galois representation just using traces from that theorem, it says that the prime has to be bigger than the dimension. But here we have that the prime is 2 and the dimension is 2. So I can't just use traces to completely determine this Galois representation. However, I can do a little bit because sigma has trace 1 mod 2. So then I can figure out that whenever I have a trace of Frobenius that is 1 mod 2, then I know that Frobenius landed in an element of order 3. So I can at least figure that out about my Galois representation. So I can use my formula. I take P, the number of elements, mod P, and then compute the trace of Frobenius. And for 5, there are 6 elements. I computed, and it turns out then that P plus 1 minus the number of points is 0. So I don't know where P lands. P equals 5 lands either is trivial or of order 2. but I don't know where it landed. I can do a little more investigation because you can compute where Frobeni element land in the Galois group of an S3 extension. You can actually compute that using probably what Keith taught you, but I'm not going to go in there. I just want to use the theory of elliptic curves. So for 7, it turns out there are 7 points, mod 7, and therefore p plus 1 minus the number of points is 1. So 7, I know that actually the Frobeni element lands in an element of order 3 in my Galois representation. Okay. Similarly, for 13, minus 5 is 1 mod 2, so it also lands in an element of order 3. But I would have to do a little more work to know whether the Frobenius at 5 lands in a trivial class or it lands on a class of order 2. Okay. And those, remember from Keith's class, I mean, it's important to know that if you want to know how primes ramify and these extension and other things that these are Frobenius elements, the order of a Frobenius element gives you. But at least we can figure out what happens with elements of order 3. Okay, so let me go through more properties of Galois representations attached to elliptic curves. So the first very important property, it turns out that the determinant of rho, so rho, the adelic Galois representation is giving you matrices. And what are you going to do with a matrix if not take a determinant right away to see what happens? But the determinant is a hum itself. So the composition is a Galois representation. It's a hum, and this hum is a continuous map from here to here. You can prove that the determinant with the profinite topology here, the profinite topology here, a determinant is given by polynomial equations, and it is continuous. So this is continuous. So you get a Galois representation to Z hat cross. And if you remember, in one of my ramblings of the previous lectures, we said that, well, that image is abelian, and the Kronecker-Weber theorem tells you that any such image has to be encoded in the one we know, in the cyclotomic one. Well, guess what? This is the cyclotomic one. So it turns out that if you do the composition and take determinant, you get the cyclotomic representation, the adelic cyclotomic representation. And similarly, if I go down to the elladic Galois representation, I can take determinants. The composition through there gives you the elladic cyclotomic character. And if you go this way, it gives you the mod L cyclotomic character. The two ways of seeing this is, one is through class field theory, that you figure out that this is an abelian representation, so it has to be but it could be some power of the cyclotomic character. It could be something that is not exactly the cyclotomic character on the nodes. But it turns out that I'm going to write some very brief reasons here for what I say. And the Weil pairing, the existence of the Weil pairing, you can prove that this is exactly the cyclotomic character. Yeah. All of these commute. Yes, you could go determinant and then reduce, or reduce and then take the determinant, and everything commutes. It's all super nice. Yeah. Very good. What else? I talked about irreducible representations. It mattered because of the Frobeni. It matters whether you have an irreducible representation or not. So by the way, an irreducible representation is such, or a simple, that it doesn't have any non-trivial sub-representation. So there is no, if you think of representations in terms of modules that have an action of Galois, there should not be a submodule, a non-trivial submodule, where Galois also acts just on that submodule. That's irreducible. Absolutely irreducible is that if you we're talking about an elladic one or a mod L, if you extend to the algebraic closure, if you extend the coefficients of your matrices to the algebraic closure, is still irreducible. There's still nothing happening in there. Okay, so it turns out that this is, for example, I believe it's shown in the book by Serre on abelian elladic representations, that these representations, the elladic representation, is always absolutely irreducible for all the primes L, and a mod L representation is irreducible for almost all L. Here's an example of an representation here that is not irreducible mod 2, because there is a point of order 2 defined over Q, namely 1, 0, and then 1, 0, because the coefficients are rational, Galois will only send it to itself. So that's a module inside the 2 torsion. That's a submodule that is invariant under the action of Galois. The action of Galois is trivial there. It sends P to itself, but that's not what matters. What matters is that there is a submodule where the action is trivial. This doesn't, you don't need to have a complement, so it doesn't have to be like it's irreducible if there are 2 pieces that are invariant. As long as there is 1 piece that is invariant, then that means that it's reducible, okay? If there are 2 pieces that are invariant, then it's semi-simple. It decomposes, so it's a direct sum of invariant pieces. That's something else. All right, so so here it turns out that mod 2, the mod 2 representation is not irreducible. Now, if you jump to the mod 4 representation, that's already irreducible. And if you jump to the two-adic representation, that is irreducible. Okay, there is no module of, like, there's no element of order 4 that is fixed by the action of Galois. If there was a point of order 4 defined over Q, then that would be some submodule that you can split out. In a sense, yes, because, like, I mean, inertia will have to, you have inertia subgroups, and if it is ramified at those primes, it will be a subgroup of this. So it sort of tells you, like, there's a whole, you know, a lot of work on that, on like where does inertia land. Once I know what the image is, what are the possibilities for the images of inertia? How big is inertia going to be if it is ramified? And that is all I think I mentioned at some point when I was defending inertia. And in much of my work, that's what I do. In much of my work, I've been trying to compute how large is a division field. And I don't know about much else other than where does it ramify? Because if it ramifies, I know much about inertia. I know how big inertia is in that division field. And then I can say, well, it's at least this big because there's all this, I know there is this much ramification. So that's a degree that the division field has to be at least that big. Okay. So what else about irreducibility? It turns out that if L is bigger than 163 for elliptic curves over Q, then every mod L representation is also irreducible. This follows from Mazur's theorem on the isogenies of prime degree, a big milestone, which actually proved, that was the last step to prove the classification of the possible torsion subgroups over Q. Why are isogenies, by the way, isogenies are homomorphisms between elliptic curves. Why are isogenies related to torsion? Well, if you have a subgroup of order L inside the L torsion, then you can do a reduction. You can do, this is a group, so I can do E mod that subgroup, and there's no priori reason to believe that this would be a curve. It's a group, but why would this be a curve? It turns out that looking at the function fields, you can prove that this is also an elliptic curve, and then you get an isogeny between E and this other elliptic curve E prime. If that subgroup is actually invariant under the action of Galois, then you get an isogeny that is actually defined over Q. And if you have a point that is a subgroup that is Galois invariant, then what happens is that if you put your Elliptic or your mod L torsion in terms of the basis P and then choose some other Q, P has to be sent to either itself or a multiple of itself. So what you get is in that, with respect to that basis of GL2 or that basis of EL, the first vector will be a star comma 0 because P is sent to a multiple of itself. And Q, who knows where it's sent? But the thing that matters is that the representation is of this type, is what we call Borel. So, and then this happens reversible. If your image is of this type, then the group generated by P is Galois invariant, and therefore it gives you an isogeny of degree L defined over Q. So there is this relationship. So if you what Mazur proved is that the largest prime degree of an isogeny over Q is 163, and therefore all mod L representations with L bigger than 163 have to be reducible. Yeah. Yes. So 163 is a prime that shows up often in number theory because it is the largest. So if you look at quadratic, an imaginary quadratic fields, Keith is giving me the thumbs up because I usually say imaginary, I say quadratic imaginary, but he yells at me. So for imaginary quadratic fields, the last one that is of class number 1 is Q adjoint the square root of minus 163. And it turns out those two are connected because the elliptic curves with CM, with complex multiplication that I'll mention in a moment, they have to be complex multiplication by a quadratic imaginary field. When they have complex multiplication, there is an isogeny. If they have CM by Q adjoint the square root of minus P, there is an isogeny of degree P for the elliptic curve. So if there were more quadratic imaginary quadratic fields of class number 1, then there would be more isogenies. So the last few primes where there is an isogeny, by the way, rational isogenies or isogenies with a cyclic kernel defined over Q are completely classified now. There's a full classification, which is really useful in applications. And the last few primes where there are isogenies are all related to CM elliptic curves. The largest isogeny that happens for an elliptic curve without CM is degree 37. All right. So a couple more results here about irreducibility. If your elliptic curve is semi-stable, which is that conductors are square free, which actually means that every prime is either good or the reduction is what we call bad multiplicative, then it turns out that there are no isogenies of degree bigger than 7. And if it is semi-stable, and you know that the mod 2 representation is trivial, so all the 2 torsion, for example, is defined over Q, then all those are conditions. Whenever you put a condition, this is not something that is very common in number theory, that sort of like primes tend not to talk to each other. But an elliptic curve, they do talk to each other. And if your elliptic curve knows too much about the 2 torsions, so in this case, all the 2 torsion is defined over Q, then the other primes hear this and then they behave very difficultly. So what it means is that actually, if you have that property that all the 2 torsion is defined over Q, then there is a number of isogenies of order 2 of degree 2, and then what it means is there are no isogenies of degree bigger than 3. All right, that is there is for the classification of what degrees of isogenies are possible. That was a theorem also that culminated after a lot of work with Mazur, for example. But what degrees are possible for isogenies was a big theorem of Kenku that is, again, very useful in applications. All right, so what about the image of a Galois representation? So if E does not have complex multiplication, that means that the endomorphism ring is just the integers. The endomorphism ring of an elliptic curve can be the integers, which are the multiplication by n maps in the group. Those are endomorphisms. If there is more than those, it's isomorphic. Then ring is isomorphic to an order in a quadratic, in an imaginary quadratic field. But so if there is no complex multiplication, then it turns out that the elliptic image is surjective. So all of GL2, the image is all of GL2 over ZL for all but finitely many primes L. Why? Because what we call Serre's open image theorem, which says specifically that if you have an elliptic curve over a number field that does not have complex multiplication, then the image is actually an open subgroup of GL2Z hat. But we know that profinite, these topological groups, open means finite index. So it's a very large subgroup of GL2Z hat. And we'll talk a little bit about what is that index. Well, For now, I'll tell you that if E has complex multiplication, then the index is actually infinite. The image is a lot smaller. For an elliptic curve with CM, it turns out the image is almost a billion. It's some sort of like generalized dihedral group, in the sense that if you go up to a quadratic extension, if it has CM by an imaginary quadratic field K, if you go up to that extension, then the rest of the Galois representation or the rest of the field of definition of the torsion is a billion over K. So it's almost a billion. That's what I mean, that up to a degree 2 extension, the image is a billion. So it's a lot smaller than GL2Z hat. All right, hopefully I'll get to describe that a little bit. So Serre's open image theorem, what tells you is that it's an open in GL2Z hat, the index is finite, and therefore every one of those projections, almost all of them have to be all of GL2 of ZL, because if infinitely many of them were not, the index would balloon to infinity. So only finitely many of them are allowed to be contained but not equal GL2 ZL. And then Serre asked in that same paper a very leading question that has been, so this was proved, Serre's paper is from 1972. And since we've been obsessed with this question of Serre, many of us, which is there a bound where that surjectivity is uniform for all elliptic curves? So is there a bound such that if L is bigger than that number, which should depend on the number field, for example, for Q, if L is bigger than that number, is the Galois representation, the elliptic one, surjective for all primes bigger than that constant for all elliptic curves? And we don't know the answer to this. It's frustrating. But Serre ventured in that same paper, is n equals to 37. I told you there is a 37 isogeny over Q, so it has to be bigger than 37. Is it 37? So for any prime bigger than 37, every representation of elliptic curves is elliptically surjective, and therefore mod L is also surjective. We don't know. We believe this to be true, but Serre formulated it as a question. And do you know when did Anna defend her thesis? What year? Do you know? So anyway, one of our Anna Medvedovsky, who was here, one of the special lectures, Serre was on her committee, and she called me for the committee before her exam. She's like, "Could you drive Serre to my exam?" And I was like, "What? Yes, yes." I get to meet Serre, and I drive him around in my car, in my Prius. Amazing. Yes, absolutely, yes. And I knew I had a question for him, which was, is Serre's uniformity question still a question, or is he willing to put it as a conjecture? And I asked him, and he said, no, it's a question. Like, there is no reason why to expect, there is no heuristic argument or anything to expect that this question should be a yes, okay? So in 2015, last time I asked him, he insisted it was a question. Some people write it as a conjecture, and it's been conjectured by other people, but I wouldn't say, well, Serre said it's a conjecture, it's a question according to Serre. All right, so if L is bigger than 5, this point is that if L is bigger than 5, if the image mod L is already all of GL2, then the elliptic image is all of GL2. So actually for 2 and 3, there are some nasty examples that you have to be worried about. For L bigger than 5, you can just check. If you check the surjectivity mod L, then you know the surjectivity elliptically. If it is not surjective, what are the possible images? Well, the possible images actually, well, the image mod L will land in GL2FL, so you can ask a group theorist, what are the maximal subgroups? Because the maximal, not all of it subgroups, because if it's a subgroup, then it will land in one maximal subgroup. So we can classify our search for non-surjective images according to the maximal subgroups of GL2. So the possibilities is that, well, yes, that is what we call full or surjective. The other possibility is that the image is Borel, if it is Borel, then we know there is an isogeny. But Mazur tells us that 163 is the largest possibility for this case. So when Mazur proved his theorem on prime isogenies, he checked off this case that there are no, at least beyond 37, every example is a CM elliptic curve with some isogeny of some sort. And in fact, there are no cases like this beyond 163. Great. The normalizer of a split cartan is another one of those maximal images. They look like this. So this is a split cartan, and you have to put these matrices also for the normalizer. And it can be a subgroup of this type of image. This was proved in the last 10 years, I think in 2011, I believe. Parent and Bilu and Parent proved that this cannot happen, that there is a bound such that beyond that bound this cannot happen. And then with the help of Rebolledo, they lowered it to, at most, it happens for p equals 13. And then a group of mathematicians, which Jennifer Balakrishnan, who is one of the organizers of this conference, they proved that for 11, actually, there's no normalizer of non-split cartan, and the split cartan, or I'm getting this backwards. Yeah, so the split cartan does happen for 11. I think there was like 13, but then 13 was discarded also. So normalizer of a split cartan only happens for primes up to 11. Okay, so by theorem of Bilu, Parent, and Rebolledo. And then the normalizer of non-split cartan is the case that we don't know yet. And Balakrishnan and co-authors, they proved that it does not happen for 11. It does not happen for 13. It can it does not happen, and now recently we also know that it does not happen for 17. Okay, so in any case, this is also the non-split cartan. That's an abelian image, and that actually in one of my papers we showed that this cannot happen also for some larger primes. And the only other option is that there is an exceptional subgroup. So an exceptional subgroup is an image such that when you reduce your image to a projective image in PGL, that image is isomorphic to A4, S4, or A5. For some reason, this is one possibility for elliptic curves. Over Q, only the projection being S4 happens. And the last prime where this happens, this was actually shown by Serre himself, that can only happen up to 13. So beyond 13, we don't think there is anything else. So if you go back, all these possibilities, it's a normalizer of non-split cartan that we don't know yet how to prove that there is no primes, there's no elliptic curve without CM with that image. The largest I think we know is up to 17. We've sort of classified what can happen beyond 17. We don't know if there's more non-split cartan images, normalizer of non-split cartan images. So that's where the status of that Serre uniformity is. Okay, so then once with all this in mind, Sutherland and Zywina, I think in about 2017, independently, they conjecture what are exactly all the possibilities for mod L images. And it turns out there is, for CM or non-CM, the conjecture is that there is exactly 63 possibilities. Among all primes and all type of images, there is exactly 63 possibilities. And if you go to, for example, Drew Sutherland's website, there's a paper on computing images of Galois representations. In the tables at the end, it tells you exactly what all those 63 possibilities are. Okay, so what can we say about the adelic image? Well, that is the whole field now is we're trying to not only do the mod L images, we're going to talk about Elliptic images, and then we're going to try to talk about adelic images. So adelically, this actually goes to a question which we call Program B in a paper of Barry Mazur, which is classify what are all the possible images for elliptic curves for Q of the possible images in GL2Z hat. There's a funny thing that is actually there's no Program A. We call it Program B, and everyone is confused because like also what was Program A? There's no Program A. This is a paper that the sections are Section A, Section B, and in Section B is this program, but Section A is about something else, about Galois representations. There is no question there. Okay, so here's an example, for example, of an image in GL2Z hat. This elliptic curve, it's very peculiar because there is the image elliptically is GL2 of ZL for all primes L, which is great, but adelically it is not. Adelically it is not because there is a conflict, there is a coincidence of two fields that are in different towers, different elliptic towers. What happens is in the two-adic tower, you have a quadratic extension of square root of minus 43, and in the 43rd adic tower, that also is there because it turns out that that is inside the cyclotomic field of degree 43 and the 43rd cyclotomic field, which is, by the way, one of the properties when I talked about the determinant being the cyclotomic extension. Something that is an outcome of that is that the cyclotomic extensions are inside in the division fields. So in any case, in the 43rd division field, the 43rd cyclotomic units are in there, and therefore this is in two places. And that gives you that the index, modulo 86, the index is already 2 in here, so it is not possible that the image of rho is all of GL2Z hat, so it has at least index 2, and in this case is exactly index 2. And Serre proved that this happens all the time. Like every elliptic curve has one of these entanglements, we call them, and the index is at least 2 every time. It turns out that then like people prove that there's this result of Hilbert's irreducibility. It's useful in these kind of settings to prove that 100%, it turns out that 100% of elliptic curves, the index is exactly 2. So if you pick an elliptic curve at random, the index is 2. However, this is the kind of theorem that doesn't give you a way to compute any single example. So I can't give you a family out of that, of elliptic curves of that form. And one of my students, my first graduate student, Harris Daniels, actually proved that he gave a specific and an explicit family of elliptic curves where the index is exactly 2, which is a family of semi-stable elliptic curves. Okay, so what do we know about the index? Here is Serre's open image theorem. We've talked about that. This is Serre's uniformity. Zewina has conjecture, actually sort of it follows. If you assume Serre's question, then this is a theorem that if E doesn't have CM, then the indices that appear infinitely often are exactly those in this list. There are some bigger indices that happen finitely many times. So there is a finite set of J invariants with a larger index. But the indices that happen infinitely often are these. So the largest index that happens infinitely often is 1536. What can we say about elliptic images? In 2014, Jeremy Rouse and David Zurich Brown proved a theorem that I was blown away that this was even possible. During the conference, in the very last talk of the conference and throughout the conference, people have talked about modular curves. To be able to prove a theorem like this, where they classified all the possible two-adic images, what you have to do is to classify essentially all the rational points on all modular curves of level a power of 2. So this is so far-fetched that if somebody had told me, oh, they're going to try to do this, I would have said, well, that's impossible, because there are modular curves there of genus 47, and at the time we had a hard time finding points on modular curves of genus 2 or 3. So This was amazing that they actually completed the classification of all two-adic images without CM. They completed the entire classification of two-adic images. And not only that, they put out, if you go to Jeremy Rouse's website, there's a database of all the images with explicit generators and explicit descriptions of what elliptic curves are in that image. And a magma program that if you give an elliptic curve, it tells you what is the two-adic image. It tells you everything about two-adic Galois representations. That year, actually, I was going on sabbatical to Madrid right before they posted this on the archive. So I went to in Madrid. I was meeting with a mathematician there, Enrique González Jiménez, and I literally arrived with a copy of their papers that this just came out. This is an amazing theorem and it has to have amazing applications. And we wrote 3 papers just using this over and over again. And the classification of rational isogenies, because it's just an amazing thing. Once you have this, you can do a lot about many things. And not happy with this, in just last year, building on the work of Sutherland and Zywina and mod L representations, Jeremy Rouse, Zurich Brown, and then with the help of Drew Sutherland, now they have classified all the elliptic images, almost. So what are the possibilities? This is Jeremy Rouse and Zurich Brown's result. There are 1,208 possibilities for two-adic ones. So if there's a star, you have to assume Serre's uniformity, but a form a little bit stronger, where not only the normalizer of non-split cartan images are unknowns, but there's a spattering, like there's another 9 possibilities or something like this that are conjecturally, there's no other point. So if you assume that there are no other ones through this conjecture, then three-adically, there's 47 possibilities, 5-adically, there are 25, and so on. And 37, there are 3, and any other prime, there is exactly 1 possibility, which is all of GL2 of the elliptics. Great. And again, they are all wizards of computation and data management. And in the LMFDB, you can find these images. So if you go to an elliptic curve, you can click on elliptic image. So if there's an elliptic image that is not full, then you can see what the image is. You click on it, and this knowledge node comes up, and it tells you exactly what are the generators. Those cannot be the generators. The image has to be an open subgroup. So what you actually have to think, this is the, you have to, they generate those topologically. These are the topological generators of that image. All right, very good. So we have in GL2 Z5, it tells you exactly what kind of image is this. So in this case, for example, if you reduce this image, it tells you that this image is 1 mod 5 here, 0 mod 5 here. So this image tells you that this elliptic curve has a point of order 5, but is actually also 0 mod 25 here. So what it tells you is that there's a 25 isogeny. So you can learn a lot about the elliptic curve itself by understanding what the image of the Galois representation tells you. All right, just very quickly, there's been a lot of theorems where it said, what about something, but not in the CM case? You know, if the elliptic curve is not CM, then blah, blah, blah. Well, in the CM case, that's what when I saw their paper, Rouse and Zurich Brown, I wanted to know what is exactly what happens in the CM case and describe them precisely. So I got to work on that. So this is a theorem of mine where I classified exactly what are all the elliptic images in the complex multiplication case. So it turns out that in the two-adics, in addition to the ones from Rouse and Zurich Brown, there's 28 more possibilities which correspond to the CM elliptic curves. And then you can check what happens for 3 and for other primes. It turns out that, for example, for 7, there are 6 possibilities. And I've given you here an example of LMFDB labels of elliptic curves that achieve each one of the possibilities for the 7-adic images of a CM elliptic curve. And I can do more than telling you exactly what happens. So it turns out the elliptic curve with CM, the CM is by orders, and these are all the possibilities for orders. where there is CM. And if you follow across, then it tells you what are the possibilities for each order. Actually, the possibilities are a little bit different. So it tells you what the possibilities are by CM order in the paper that is in the archive. Will appear soon in Algebra and Number Theory. For example, when the discriminant of your order is -8 and the conductor is 1, so this is the maximal order, and you look at the two-adic images, these are the possibilities for the two-adic images. So it's images generated in GL2, Z2 by those matrices. Okay. So, and again, these are topological generators. So anything that is close enough to this is also in the image. And these are LMFDB labels for those elliptic curves. And there is also in the LMFDB, they keep track of number fields. So this is actually the mod 16 image. Oh, this is not a number field, but a label for a group in GL2 Z mod 16. So you know exactly what image that is. Very quickly, if you have an elliptic curve with CM, then there is CM by a quadratic imaginary field. What that means is that there is a ring of integers and a conductor in order that your endomorphism ring is going to be isomorphic to that order. And then there are J invariants that are attached to that order. Those orders depends what the class number of that order is, what that number field will be where the elliptic curve is defined. So you have elliptic curves for each one of those orders. There are J invariants and elliptic curves defined perhaps over a number field with that CM. And what I did in that paper, so before this paper, this is the kind of thing that experts, this is exactly what Lillian Pierce was talking about today when she was talking about the essential number theory. If you asked before this experts, what is the image of a Galois representation attached to an elliptic curve with complex multiplication? They would tell you it's a normalizer of a cartan subgroup in GL2 Z hat, you know, and it just follows from the theory of complex multiplication. But there is an index. It's not all the normalizer. There is an index that divides 4, divides 6. And what the actual image is was not written anywhere. I'm sure people could compute it, but nobody had actually gone through, computed, and then analyzed exactly how many possibilities are there up to conjugation and so on. So that's what I tried to do, compute all those. So I'll just leave it at, so it turns out you can define what I said. There's some sort of cartan subgroup, a generalized cartan subgroup, and a generalized normalizer of cartan. And then if you do the inverse limit of those, they give you a, again in quotes, a normalizer of cartan in GL2 Z hat, and every image of a CM elliptic curve lands there. And again, if you go up to a quadratic extension, then the image is inside here, so it's a billion. So that's why these images in GL2 Z hat are sort of small. But again, one can classify, and I did classify all the possibilities for these elliptic images, and for example, again, for discriminant 4 and conductor 2, these are the possibilities of the images that occur. Thanks to Drew Sutherland, we came up with a labeling system of those images, so that hopefully will be incorporated into the LMFDB soon. Also, these type of labels for CM Galois representations, and these are examples of elliptic curves with those 5 types of images that occur in this case. So I think I'll stop there because I'm already over time, and thank you so much for your attention.